Today, we'll just talk in broad strokes, since it's just the first class, about what regression is and why you should use it. And I'll go through a lot today, but I'm going to go through it all slower again in future classes, so it doesn't matter if stuff slips by. I'm going to start a little bit mathy, but then back up and do clear examples. Okay, so what is a regression? Regressions are methods to use data to try to estimate conditional expectations. So what's a conditional expectation? It's what you expect the value of an outcome to be, given that you've observed or conditional on observing certain values of predictors or covariates or features, all different names for the same thing. So in mathy notation, the conditional expectation is expectation of y, vertical line. So y is the outcome, and the predictors and covariates are all these x's. So the conditional expectation of y, given that you observe that all these x variables, x1 through xp, big X1 through big XP, take values little x1 through little xp. And a regression function is a function of the covariate values, like little x1 through little xp, that are inputs to the function, and then the function outputs what you expect the outcome to be, given that you observed those values for the predictors. And the goal of regression is to learn this f function, or try to get a good approximation to what it is. So a function that would actually give you what you expect the y to be, or like the average value for the y, the outcome, given values of the predictors. Let's start with an example. Here's data on flippers, penguin flippers, for 3 species of penguins: Adelie, Chinstrap, and Gentoo. Each dot is a different penguin, and on the y-axis is their flipper length in millimeters, and you can see there's variation within each species, right? So what is the expected flipper length conditional on penguin species? So what would be a natural way to go about answering this question? So the estimate of the conditional expectation of flipper length, given that the species is just 190, which is the center of the dots of the Adelie penguins, right? And with Chinstrap, it's 195, which is also the center of the dots. And with Gentoo, it's 217. And again, center of the dots, just the average of the dots. So this was a regression function, right? It takes as input the predictor, which is the species, and it outputs the expected flipper length for that species. So it's a conditional expectation function. So what is f here? Like where f from the previous slide was the regression function that we're trying to learn. Can you think of maybe a way to write f or express it as a function? So the regression function here is 190 times a variable which is 1 if the species is Adelie and 0 otherwise. That's what I mean by this delta sub-Adelie thing, plus 195 times delta Chinstrap, so an indicator for whether you're a Chinstrap penguin or not, plus 217 times an indicator for whether you're a Gentoo. So that will give you, everyone's only one species. You're just going to get one of these numbers. And so whatever species you are, you'll be assigned to the average flipper length within that species. So that's a very simple regression. And even though it's very simple, it completely embodies what regression is. Regression is this simple. It's just you have inputs or predictors, in this case it's species, and you want to know the expected value of the outcome given a value of the predictor. In this case, it's what species are you, and you want to try to learn that function. And in this case, it was very simple. You just took the sample average of the outcome within each level of the predictor variable. Here, the predictor was categorical, right? It just had a bunch of discrete values. It can get more complicated, but the idea is the same. And the mechanics of it can get more complicated, but the idea is always the same. It's just, what do you expect the outcome to be given that you observe certain values of the covariates? So here's another example. This is from the book Regression and Other Stories, which I wouldn't say it's the textbook for the course, but it's the source that I'll most often refer you to as supporting material to read if you want to either go more in depth or just reinforce what's said in lectures. This figure depicts data from an experiment where students were randomly assigned to either watch some educational television program called The Electric Company, which I haven't heard of, or not. And children were then given a reading test after they either did or didn't watch this television program. And the data are split up by the grade of the kids. So this experiment was conducted in kids in grades 1, 2, 3, and 4. And the control classes are ones that didn't watch the television program, and the treated classes are classes that did watch the program. And the black vertical lines are the averages within each cell. So this is like the penguin flipper example. It's just that instead of just 3 penguin species, we're now splitting things up both by treatment and by grade. So we have 8 categories where before we had 3 categories. But you can, again, just look at the average within each category of the outcome. And just eyeballing this, it seems like the television program does improve reading abilities for children in younger grades, so in grade 1 and grade 2, but not so much in older grades 3 and 4. Here's another example of a regression from Regression and Other Stories. This one is looking at the relationship between average recent growth in personal income and the incumbent party's vote share in the presidential election. So each data point is a year, and you can see that the higher the average recent growth in personal income, the higher the vote share of the incumbent party, where if it's above 50%, you win. And there's a very strong relationship here, right? If people tend to be doing well personal income wise, more of them tend to vote for whoever is currently in power. So now we have, instead of a categorical predictor variable, we now have a continuous predictor variable, right? So whereas before, when we were trying to see what's the expected outcome for a given value of the predictor variable, we were just taking the average of all the outcomes that had that predictor variable, right? That had that value. But now, for any given growth in personal income value, there's at most one election where that exact value was observed, right? So you're not going to get a reliable estimate. And for many, there's 0. If you wanted to know what would happen for 1.3%, say right here, there was never an election with that exact recent growth in personal income. So now you need a model to extrapolate a little bit or interpolate between points where you actually do get to observe outcomes. So in this case, the assumption was made that the regression function was linear, that it was a straight line. So the assumption was made that for a given recent growth in personal income, the expected outcome, the expected incumbent party's share, can be expressed as a linear function of personal income. And using methods that we'll learn later in the class, they find that the line that best fits this data, that best runs through these points, which we'll, again, make more precise later in the class, is that incumbent party vote share is 46.3 plus 3 times the recent growth in personal income. So that's just another example. Okay, here's a crazy one. This is something that we won't be doing in the class, but just to show that regression can run the gamut from very simple, like the penguin example, to very complicated, like this, but it's all the same idea. Here, the predictors are pictures, and they're pictures of skin lesions. And the goal is to diagnose melanoma. And so here the features are super complicated, right? It's like pixels. It's a list of pixels in a picture. And they needed to be represented by being run through a neural net before they're then fed into a tree. But still, it's all they're doing in this very complicated process is trying to find the conditional expectation that a particular picture is melanoma, given its pixels, given what the picture was. we won't be doing fancy regressions like this in this class. We'll focus on simpler ones, linear or logistic. But I just want to emphasize that it's always the same idea. Okay, and here's an example of regression gone wrong. So this is like a self-driving car, and there are people riding in it, monitoring what the self-driving car thinks is in front of it. And it's driving through Amish country, and there's a horse and wagon in front of it, which is something that has never appeared in its training data before, right? That's very unusual. And so what it thinks is in front of it is a person walking in front of a car. And it cycles between, if you watch this video, thinking that versus thinking it's a truck coming right for them, which it does look like too, right? The back of this wagon looks like the front of a truck. So this is regression gone wrong. This is trying to find the conditional expectation of the outcome, which is just what is the thing in front of the car, given, again, it's like pixels or video, a complicated set of predictors. But when the predictors are not things that you've ever seen before, you're kind of making guesses based on outside of your data set. Regression can go wrong. Okay, so here's an example of it going. So what are the types of things you can do with regression? Regression is a very flexible tool, and it's a tool that can be used to do a lot of things. One thing you can do is prediction. So given covariates, the conditional expectation of the outcome is a really good prediction of what the outcome will be if it hasn't happened yet. One example of this would be prognosis. So for a medical condition, if you look at the person's symptoms and vitals and all the information you have about a patient, you can predict the prognosis of a disease. Or if you look at the examples of regressions that we've already done, the election economy thing could be thought of as a prediction, right? Or it could be used for prediction. Like before an election occurs, you might already know what the average recent growth in personal income was. And then you could use this regression model to then predict what the incumbent vote share will be. Another thing you can do with regression is classification. So maybe you're not trying to predict the future, but you still have an unknown outcome, for example, a diagnosis. So you have symptoms that you get to observe, and you're trying to classify what the condition was that led to those symptoms. And again, an example that we saw there would be diagnosing melanoma. Sorry, just going back to prediction. In this regression, where you had the educational television show that was given to different grades or not, you could use a regression to predict what somebody's reading score will be given their grade and given whether or not they saw the television show. You could use it for pure prediction there. Another possible use for regression is to identify risk factors, or just to identify variables that are strongly associated with an outcome and quantify how strongly they're associated. So this is just description. It's describing associations that are out there in the world. And again, the economy and the election example could fit under that category as well. You're showing that there's a very strong association between personal income growth and election outcomes. The penguin flipper example could also fall under this category. And it could also fall under prediction. You could predict a penguin's flipper length given their species, or you could see that species really does have a strong relationship with flipper length, right? The gentus really do have bigger flippers. So that's a descriptive result from a regression. Another thing you can use regressions for is extrapolation. So let's say you have a particular sample, and maybe you have a disease prevalence in your sample, maybe a survey, and you want to estimate what is the prevalence in the population, not just in your sample. You're more interested in the population. Regression is a tool that you can use to go from sample to population. The challenge being that if your sample is not a simple random sample of the population, you need to correct for that selection bias for who actually did participate in your survey, for example. And regression is a tool that you can use to do that. And then finally, causal inference. So in causal inference, the question is usually, what if everyone had followed a certain treatment strategy of interest? What if they had taken treatment A? What if they had taken treatment B? And regressions in this case can often be used to adjust for confounding. They can also be used to quantify effect heterogeneity. I guess which of these regressions that we looked at do you think would be potentially good examples of regressions that might be used for causal inference? So to refresh your memories, there's the penguin flippers, there's the education experiment, there's the personal income and election and incumbent vote share, melanoma diagnosis, and self-driving car, but forget that one. Are there any that you think might be particularly useful for causal inference? That's definitely one that could be causal, right? You're not using the regression to adjust for confounders there because there are no confounders because it was randomized. We'll get into that later. But yeah, this regression can certainly be used to compare the mean reading score in control and treated. And then that can be interpreted as the effect of the class. And the regression can also be used to show how the effect varies based on covariates, where here the covariate that it varies across might be grade, where we see that there's a stronger effect in the lower grades. In the penguin example, based on prior belief, I think it probably makes a lot of sense to think that the difference in flipper lengths across species are because of a species, like it has to do with the genetic differences between species, but it could be confounded, right? Maybe a certain species lives in a certain area where there are more fish and they can get bigger or something, right? And if they lived where the gentoos lived in the fish poor areas where the Adelie and chinstrap lived, they'd have smaller flippers too. So maybe it's not causal. Similarly, there's a kind of a clear causal story that we can tell about why it would make sense that as personal income growth goes up, incumbent party vote share goes up. But there could easily be confounders there as well. So it's not necessarily causal. So we should learn about regressions to be able to do all of these things, right? These are all useful things to be able to do: predict, classify, describe, extrapolate, and estimate causal effects. And you'll use regression in different ways to do these different things. But then also so that you can assess how well other people are doing these things. A lot of people just throw a bunch of variables into a regression and interpret the results as if they've estimated a causal effect or extrapolated or described. But you want to be in a position to be critical of what their claims are based on a regression. So both to consume regressions as a more informed consumer and also to be able to do this stuff yourself. Those are the main motivations to learn about regression. One thing to keep in mind is that regression can be used for all of those things, but all of those things don't necessarily just amount to doing a regression and then interpreting its output. So sometimes regression is just one cog in a larger machine to achieve causal inference, let's say, or extrapolation. You need to fit a regression to do that, but it's just one part of a larger process. So we'll go over some examples of that. And so yeah, pictured is Charlie Chaplin is you working on your R code to fit a regression, which is part of a bigger machine to maybe estimate a causal effect. Here's an example of regression as a cog. And again, we'll go into this in more detail later. It's fine if you don't internalize this the first time through. But in causal inference, often what we care about is the expected counterfactual outcome had everyone taken a certain treatment. So let's say y of 1 is what someone's outcome would have been had they taken the treatment of interest. So had everyone watched that reading video, what would be the average reading score? In reality, not everyone did. So this is the thing that we care about. And this is what we want to estimate. And it can be shown that this thing, even though it's counterfactual and you don't get to observe it because not everyone really did watch the video, under assumptions, it can be expressed as the sum over covariate values of the conditional expectation of the outcome, given that the treatment was observed to be 1 and that the covariate value was little x times the probability that the covariate value is little x. So it's the sum over x of this thing. And this is a conditional expectation right here, right? So it's a regression, or you can estimate it with a regression. But that's not the end of the story, because you need to embed it in this larger sum to get the causal effect. So this is an example of regression being a cog in a machine to do what you care about doing, but not being the extent of the machine itself. And that's why in causal inference, often this is called the outcome regression, is sometimes called a nuisance function, because it's not what you really care about, but it's something that you need to estimate to get at what you really care about. I think that's a little mean to regressions to call them just a nuisance, because they're really the engine of the machine that you're building to get what you want. So that's the end of the broad introduction to regressions and why we should care about them.